Okay, so welcome back to our video. So here, today's video is going to be a short one, and I say short despite our integrand looking a little bit intimidating for all these inverse trigonometric functions. So we have the definite integral from 0 to 1 of the inverse sine of cosine of x plus the inverse sine of cosine of x times the inverse cosine of sine of x plus the inverse cosine of sine of x, all being divided by inverse sine of x plus inverse cosine of x quantity squared dx. So intimidating as it seems, there's actually a trick that we can actually reduce all this down to a simple answer. So that's actually relying specifically on the right angle triangles properties, or the symmetry for the cosine and sine functions at pi over 2 of that radian. So if we actually just use that and just put that back into our substitution, and then so that'll actually make the simplification a whole lot easier. So there's nothing really much need to be said from there, because I find this integral very interesting just for the fact that it actually just looked like, for one, it's kind of scary that the process might actually take a while to actually solve this out completely, but it's in reality, it's really not. So with that, why don't we actually just jump right in. So our two functions we'll be using, so cosine of x, if we actually utilize the symmetry of the pi over 2 radians, so that's actually going to be written as sine of pi divided by 2 minus x, and same thing for sine of x, that will be cosine of pi divided by 2 minus x. So implying that if I were to take its inverse, so of course when you take inverse, sometimes you got to be careful on your range. Specifically, if I were to take the inverse of sine of x for over here, that range has to fall between pi over 2 to pi over 2 inclusive, negative pi over 2 to pi over 2 inclusive, but since we actually do this shift, so that actually changes the range from there. Same thing for over here, if I take the inverse cosine of x, so that range is from negative 1 to 1, but we have to shift from there as well because of pi over 2. Thankfully, that actually falls within our integration bounds. So what we have now, if I take the inverse, so that means I have inverse sine of cosine of x, so that means that's just going to simply equal to pi divided by 2 minus x. Do the same thing over here, inverse cosine of sine of x, so that'll also be pi divided by 2 minus x. So with this, now we can actually just go back to our original integral, so capital I, our new bounds, or not really new bounds because that's still going to stay the same, our new substitution if we actually put all this back together. So what I have now is going to be pi divided by 2 minus x, then add this with pi divided by 2 minus x multiplied by pi divided by 2 minus x, and then add this with, yet again, so pi divided by 2 minus x. And then underneath our denominator, so there's a nice identity, inverse sine of x plus inverse cosine of x. That is going to equal simply just pi over 2. But be careful that x has to be in the range between negative 1 and positive 1 inclusive for that result to hold. But thankfully, within our integration bounds over here, that actually is valid. So I take that, so square that, so now I have pi squared divided by 4, and then dx. All right, so with all that, now we can actually just reduce some things here. So first things first, we see that, so I have the 0 to 1, and then we have combining like terms, so I have 2 then times pi divided by 2 minus x, and then add this with pi divided by 2 minus x, then quantity square, and then we still have our pi squared divided by 4. So with this in mind, so of course pi squared divided by 4, I can actually factor that outside, and so that means that will just change the reciprocal, so that will become, 4 divided by pi squared. So now continuing forward, that if I just distribute the 2 and then expand the pi divided by 2 minus x of that quantity, so let's see, 4 then divided by pi squared, so that means integral from 0 to 1. So now this actually just looks like we're reducing to just a simple polynomial over here. So now everything together, so I have pi and then subtract 2x, and then now add this, so with the expansion over here, so I have pi squared divided by 4, and then minus pi times x, and then add this with x squared, and then followed by dx. Okay. So everything from here is actually pretty simple to compute / find its antiderivative. So putting all this back together, so now 4 divided by pi squared. So now I just take the antiderivative of each terms over here. So now that's going to be pi times x, and then subtract, x squared. Add this with 4, or pi squared divided by 4 multiplied by x. then subtract pi squared divided by 2 multiplied by x squared, and then add this with 1 divided by 3 times x to the power 3, and then evaluate this from 0 to 1. And of course, if you just plug 0, the whole thing is just going to vanish. So now the only thing left is just to plug 1 in there. So 4 divided by pi squared, and then multiply. So now it's going to be pi, then subtract 1, add this with pi squared divided by 4, subtract pi squared divided by 2, and then add this with 1 over 3. Okay, so now to skip the next step, what I'm going to do is, of course, this actually just going to, all you need to do is just get this to a common denominator. You just get it for a denominator of 12, then put everything back together such that it actually falls within that nice fraction. And then if you simplify things out, this 4 will actually reduce to just a 1. So it's going to be 1 divided by pi squared, and then now multiply by, so we have 3 pi squared. This is just from all that calculations all together. So 3 pi squared, then add this with 6 pi, and then subtract 8, all being divided by 3. And then if you want to reduce this even further, so that means now the 3's are going to cancel, so it's pi squared, and then that's going to be plus 2 pi, and then minus 8 over 3. Then distribute the 1 over pi squared into here. So now what I have now is the final answer can be simply reduced to just 1, and then add this with 2 divided by pi, and then subtract 8 divided by 3 pi squared. So with that, that is actually our final answer to this intimidating integral that's really, in reality, not really that intimidating if we actually just utilize this nice property for the right angle triangle slash symmetry at the pi over 2 radians for cosine and sine. Substitute that all together, put that back in, and then it just comes down to a nice easy antiderivative to compute definite integral rather. Reduces this down to just a simple answer, just like that. So yeah, that's pretty cool if you ask me.